All right. So we are going to start a new topic today, torsion. So in this subject, at the very beginning, I said that we are studying about structural members subjected to different kinds of loads. Last 2 weeks, we were discussing about structural members subjected to axial loads. Okay. And today we are going to study another type of load, that is the twisting moments. A twisting moment that twist a member is called a torque. I hope that you heard this word before, torque. Okay, so a member, a force, or it's not a force, it's a moment, right? A moment which twist a member is called a torque. And once a torque is applied on the structural member, it is going to create a internal resistance, right, that will lead into deformations, and that deformation may affect the performance of that structural member. So there are so many structural members or parts in mechanical engineering applications where you find members subjected to twisting moments. So it is very important for us to study about or learn about, or how to design such, learn how to design such members, so that we can develop or design safe structures, safe systems. Okay, so the purpose of today's lecture is to, or I'm going to use actually 2 weeks to introduce this topic. We are going to learn about members subjected to twisting moment. Right. So this is the outline. So first, I'm going to talk about the deformations, the strains, when a member is subjected to torque or torsion, how the deformation happens, and then the measure of that deformation, the strain, and then I'm going to use Hooke's law, and with the Hooke's law, I'm going to talk about how the stresses are developed. So basically, we are going to learn about shear stresses, but there are some other stresses developed in the structure. Okay. Another measure of the deformation is angle of twist. So we are going to learn about how to analytically find out the angle of twist. At this moment, you might not understand what it is. Later, I will introduce what this is. Okay. So we also talk about statically indeterminate problems, which you can solve only using mechanics of materials knowledge. Then by combining the concepts that we have learned, I'm going to introduce you how to design transmission shafts which are subjected to torsion. Lastly, we will discuss about effect of stress concentration, which is very important when it comes to safe design of structures. Right. So several topics, but today I'm going to concentrate only first 2 bullet points. So I will introduce you shear strain, or the strain, and the stress resulting from torsion, and then angle of twist. We will do several examples so that we learn how to apply the concepts and quantify those parameters, or those important information about when it comes to design. So before I move forward, I want to emphasize that in this section, I'm going to limit my discussion to members which subject to this kind of twisting moments, and our discussion is going to restricted to members with circular cross section. There's a reason for that. Normally, if the major mode of loading is torsion, twisting moment, the best sectional shape or cross-sectional shape to resist that load is circular section. So you will understand it later. Okay. So if you use any other shape, then we need to use more materials to resist the same load. So the circular section is the optimized section, the best section to resist torsion, meaning that using less material, we can support larger twisting moment. Okay, that is the reason most of the theories are developed for circular members. And if you look at in the applications, almost 90% of the application you find circular members whenever there's a torsion or major mode of loading is torsion or twisting moment, then we use circular sections. There are other shapes as well. There are theories how to analyze those things as well, but I'm not going to introduce you those things in this subject. Okay, later with the knowledge you develop from this section, you should be able to extend your understanding to analyze those other shapes. Right. So here the twisting moment, we call it a torque, right? And it is a vector. So this is a vector. So here the magnitude of that torque is normally denoted by letter T. You can see in this diagram, there are two quantities, T and T prime. So T and T prime, magnitude wise, they are the same size. But the direction is opposite, right? The sense is opposite. That is why that the two different notations. Okay, right. So since it is a vector, there's a direction. Okay, so I will introduce a sign convention where we use it to identify the direction of this vector. So at this moment, I'm not going to talk about that. Right, let me move forward and start off developing some theoretical concepts to analyze or quantify stresses and strains. And before that, yeah, I would like to show you some application areas where you find members subjected to torsion. So if you look at a vehicle, it generates power by the engine. Engine is the prime mover, and power from the engine should need to be transmitted to the wheels. And there you can see underneath there's a transmission shaft. Here you can see it's a circular shaft with a circular cross section, and it transmit power from the engine to the wheels via this circular shaft, and it is going to transmit power by twisting, right? It rotates and it twists, and through twisting it transmit power from one location to the other, right? And there are many other components in the same vehicle which subjected to this kind of torsion. So you can see that for the steering wheel, once you steer, you can see there's a vertical column, right? That vertical one also get twisted, and then that by twisting it transmit power from your hand or the steering wheel to the wheels, so that wheel can be turned. So there, the vertical column is connected with this kind of circular shaft, and it is called a torsion bar. So what it does, it transmits again by twisting, the power is transmitted to the wheel so that we can turn it. So we can see that in a vehicle, there are so many members subjected to torsion. So we need to design them. We need to make sure that they use less materials, right? All the members should be efficient in the sense, use less materials and be able to transmit more power, right? So that vehicle is lighter and it can run long distance using less fuel. And there are some other applications like what you see here, big machine where the power is transmitted from one unit, maybe the motor, to the driven unit through a shaft like this. This is actually called coupling, flange coupling. And one is a driving shaft, the other one is driven shaft. And both are subjected to torsion. So if I show you some specific example, and what you see here in this diagram, there's a turbine and a generator. As I'm sure that in thermodynamics, you are learning about turbines. turbines generate power. They can be gas turbine, it can be steam turbines, or it can be hydraulic. That means run by water. Right? So what it does, it converts the potential energy or pressure energy in the fluid into kinetic energy. That kinetic energy then drives the generator. Generator generates electricity. So in this process, we have to combine turbine with the generator. So for that, we use this kind of transmission shaft, and that shaft is completely or purely subjected to torsion. So if you don't design it properly, it might fail while it is transmitting the power, or it may be too heavy, it may not be optimized. So the designer's job is to design this so that it will not fail. It should be able to transmit the designed power. At the same time, it should be as light as possible, economical. Right? To design this kind of shafts, we need to have the knowledge of the internal resistance created by the material for the applied twisting moment, the torque. And also, we need to know what is the deformation. Why they are important? Because let's say this member AB is made from very flexible material like rubber. Can you transmit power? You can't, right? It twists too much. So that means it consumes the energy developed by the turbine. So there's an energy loss. So it should be hard enough. It should be rigid, but should not be too rigid like glass or like cast iron, because it will break again, right? So therefore, it is the job of the designer, engineering designer, to do the calculation, find out the internal resistance created by the material once you apply the external load, and then the level of deformation created as well, and design the right size, right, and specify the right material. Right? To do that, we need to be able to quantify the stresses and strains resulting from twisting couples or torques. So that is what we are going to learn today first. Okay. So let me start with telling you very important thing, that is we need to make some assumptions, because we are going to develop theoretical equations to quantify the strains and stresses. Uh, to develop those equations, we need to make some assumptions. First assumption, we are going to assume that all the deformations are linear and elastic. That means there won't be any permanent deformations as a result of applied torque. All the deformations are small, therefore everything happened within the elastic region. So within the elastic region, the deformations are linear. That means the force and deformation relationship is linear. So that is the first assumption. Second assumption, we are going to assume that plane section remains plane and undistorted. So let me explain what is meant by that. Now, so since our discussion is restricted to circular members, so look at the diagram below. There you can see a circular shaft, and I have put a grid on that. So it seems like this member is made of several circular discs. So by gluing together several circular discs, we can make this kind of shaft. Okay. So once we apply the torque, we assume that there won't be any size changes, right? These discs going to move relative to each other and get a new position, or change the position, change the shape, but not change in the dimensions. So that means after applying the load, before applying the load, all the sections, every section, if you cut from any position, it is circular. Cross section is circular. And after deformation also, cross-section remains circular. No distortions, undistorted. And all the planes, the perpendicular planes to cross the major axis remain perpendicular. That is meant by plane section remains plane. No twisting, right? There's a twisting, but that twisting happens in plane, not out of plane. Hope that you understand what I'm talking about, right? So it's like a shaft is made of several discs, and discs going to shift or move relative to each other without any deformations or distortions. The deformation happens like position change happen, but there's no distortion of the cross section, right? Uh, to understand what's going on once we apply the torque, so you look at the first diagram where I put a grid on, and if I look from this direction, you will get this diagram, right? So this is how it look like. And then please pay attention to this blue rectangular block here. So this is how it looked like before application of the torque. So then, and also I have just drawn a line on the circular section at the end of the member. So this is the center, and it's actually the radius. Okay, and see what is going to happen if I apply a torque of T. Right? T. Maybe I'll make it to T prime to show that direction is different. Then what is going to happen? That red line I have drawn now going to shift to a new location. So with respect to the original position, it is going to create an angle, and that angle is denoted by letter phi, and it is called the angle of twist. So this angle of twist is given with respect to the other end. Right? So if I mark this position as A, this one as B, right? A, B. This phi is the angle of twist with respect to B. Right? With respect to B, it now has twisted by angle phi. So now look at that rectangular shape I have drawn in the first diagram. So what is going to happen to that? Now it is going to become like a rhombus, like this. Right? So the size or sides of this rectangular block has not changed, but it has the shape of the rectangular block has been changed into a rhombus. So there are going to be a certain angle change here, right? That angle change here, this angle here, is called the gamma, or is the shear strain, because the shape change is associated with shear strain. So what you normally see once you apply a torque, a shape change. So that means there should be a shear stress in here, and there should be a shear strain. Okay, so I hope that you can now visualize what is going to happen once you apply a torque. So let me give a little bit more information on that. So we have a let's say a circular shaft which is fixed at B here at this point, and we have drawn a line AB on the outer surface of this shaft. And now I'm going to apply this torque T to the end A, right? And then what is going to happen to line AB? The point A here now going to shift to A prime. So that means there's a displacement of the point. So displacement means there's a strain, right? So that and also it creates this angle of twist phi. This angle of twist phi going to be proportional to the size of the torque that I have applied. If the torque is smaller, the angle phi is small. But if the torque is high, angle phi is higher, right? So they are directly proportional. So that is what we can observe first. The angle of twist is proportional to the applied torque, number one. And also it is proportional to the length of the shaft. Longer the length, higher the angle of twist. So you can see that if you move towards the fixed end, angle of twist becomes smaller. And at the point B here, angle of twist is 0, no twisting at all. But if you move towards point A, angle of twist gradually increase, right? Therefore, the angle of twist is proportional to the shaft length as well, okay? And based on the initial assumption that we made, now here, no change in the cross-sectional shape. It remains as circular after deformation, right? And no distortion. So therefore, this the kind of derivation that I'm going to make now going to be applicable only for circular shafts. So if you look at this kind of shaft with a square cross section after deformation, if you cut from any section, you will not see a square anymore. It has been distorted, right? So therefore, the stress and strain relationship that I'm going to derive now, not going to be applicable for other shapes. It is only for circular shapes. Okay. So with that little observation, I'm now going to find out what is the shear strain once we apply a torque T. Right. So by looking at this diagram, you can see that initially, if I mark this point here as I use a different notation here, D, and it be moved to D prime here. So it has moved this distance. And if I take another point here with under the same torque, yeah, I'm going to apply a torque T like this. Under the same torque, point in here going to move this distance. That means the deformation is smaller, strain is smaller. So as you move along the radius in the radial direction up to the center of this circle, you can see at the center, the material at the center has not moved at all. That means no deformation. No deformation means no strain. So now can you see that once we apply a torque onto the shaft, the strain is not constant on the cross section. Strain is changing from a very high value, which is on the outer surface of the shaft, to the very small value, ultimately up to 0 at the center. So shear strain is not constant. It varies from a maximum value to a 0, right? So if I want to derive a relationship for shearing strain now, I need to uh, go into or find a generic point and do all the derivation to get that generic point, right? So therefore, I'm going to select a, a radius. Okay, so before I go any further, I need to show you that here, this radius, maximum radius, is denoted by letter C. So throughout the derivation process and even in your textbook, they use the notation C to denote maximum radius. So let me write it. This C is the maximum radius. Okay, and any radius between 0 to the maximum radius C, that means any point, radial point between 0 and C, is identified by letter rho in the second diagram. So rho is a Greek letter, you know that, right? this is any radial position. Okay, any I say any radius between 0 to C. Okay, so it's a generic point. So what I'm going to do, I'm going to take a core of cylinder, let's say it's shaft core with a radius rho, and remove all the materials outside, and then take a interior disc. So this interior cylinder right in here, and see what is going to happen to this interior disc or cylinder once I apply a torque T. So once you apply the torque T, what is going to happen? It is going to deform into this shape, right? So still at the end of the shaft, the angle of twist is phi, right? And now I just want to show you some more details. Therefore, I'm going to go to the next slide, and we'll come back to this slide later. Okay. So this is the same diagram, and I have drawn a bigger diagram just to show you a clear picture what is happening here. Right. So once I apply the torque T, the shaft has been now twisted, and I'm now considering the inner core with radius rho. So there, my purpose is to find out an expression for shearing strain. Therefore, I need to look at the deformation. So here, point A has moved to A prime, right? A prime. So that is a displacement. So that creates the strain. So can you write an expression for this A prime in terms of rho and phi? I hope that you have learned these things before. So if there's an arc A prime, like this, and this is the point O, center, and here the radius is rho, and angle here is phi. So then what is the arc length? Arc length A prime is equal to what? Rho phi. You understand that? You know that, right? Right. So it's very simple actually, because if you take a circle, right, circle total angle is 2 pi, and if the radius is r, the perimeter is 2 pi r. 2 pi is the 360-degree angle, right? Now here the angle is pi, and this is r, right? This is r. So it's rho pi. Okay, now that is by looking at the arc length A prime. Here at the very beginning, I said that we are going to assume that deformations are smaller and within the elastic range. Okay, therefore we can assume that A prime B is a triangle. Okay, so consider triangle A prime B. So it's a triangle, right? For small angles, let's say for small deformations. Now, by looking at that triangle also, can you write an expression for A prime? And before that, I just want to show you that because of the applied torque, now the rectangular block I have drawn in the diagram B now has been changed into a rhombus. And if I draw a parallel line like this, okay, this angle change here, this angle change is the shape change, and it is denoted by gamma, that is the shear strain, right? So by looking at the geometry, I can say that this angle here also gamma. Okay, so therefore now I can say tan gamma for small angles is approximately equals to gamma, and it is equal to a prime over AB, right? AB, that is a prime over L. L is the total length, this length of the shaft. Okay, so that means a prime is equal to L times gamma. So we found two equations now for a prime. This is 1 and this is 2. So 1 is equal to 2. Right? So now what we can see, L gamma is equal to rho times phi. So now you see that there's a relationship between the angle of twist and the shear strain. Right? So now, if you have already copied the things, maybe I give you 1 minute. Okay, I hope that everything is clear up to now. But I did simple geometric analysis, right? I have written two equations for a prime by considering the arc length and also a prime b triangle. Okay, then I equate them and got this final relationship. L times gamma is equal to rho times phi. So if I go back to my previous slide now, so here can you see the same thing? So this equation is derived using the explanation that I have just given to you. So this one tells me that there's a relationship between angle of twist and the shear strain, and their shear strain can be written by this equation. And for a given cross section, when L is constant, right, angle of twist also constant, the only variable is rho. So from this one, we can see that when rho is equal to 0, angle of shear strain also become 0. Oh, I say it's equal to 0. Okay, when rho is equal to c, that is the maximum radius. Sorry, my shear strain going to become maximum or gamma max, because that is the c is the maximum value that rho can take. Okay, when rho vary from 0 to c, the shear strain gamma vary from 0 to the maximum value. So there's a linear relationship, right? So shear strain therefore proportional to the twist, that is the angle of twist, and to the radius for given cross section. So now if I take one cross section, once we apply a torque T, it deform the cross section or shift the position of the cross section, and then the maximum strain happens in the outer surface when radius rho is equal to c, and if I mark that shear strain as gamma max, okay, and when this rho becomes 0, that is at the center, shear strain is 0. So in between, the shear strain vary linearly. So any point, now we can find out what the shear strain using this equation, right? And the maximum deformation or maximum strain happen in the outer surface, and at the center, there's no deformation, there's no strain. All right. Okay. So now we just learned that when rho reaches to C, gamma reaches to gamma max, and therefore I can write this equation. Okay, gamma max is now equal to, in place of rho, now I put C pi over L. Okay, and using this equation here, okay, I can replace phi L using gamma over rho, and finally I can get this equation. Okay, so here again it shows that when gamma is equal to, sorry, rho is equal to 0, shear strain is 0, and rho equal to z, shear strain is become maximum, that is gamma max. So there's a linear relationship. Okay, that is what I want to highlight here. So now we have some understanding about the shear strain, and now we'll look at the stress, shear stress. Okay, so within the elastic region, I'm going to go to the next slide. Within the elastic region, the Hooke's law applies. So our equation in it that we just derived is rho gamma is equal to rho over C times gamma max. Okay, and from the Hooke's law, we know that shear stress is proportional to shear strain within the elastic region, and therefore we can write this equation. This is from Hooke's law. Shear stress is equal to G times shear strain, and you know that this is the shear modulus, or we call modulus of rigidity, right? So now what I'm going to do, I'm going to take this initial equation that we have derived in the previous slide and going to multiply it by G, both sides, and then get this equation. G gamma is equal to rho over C times G times gamma max. And here G gamma is tau. Okay, G times gamma max is tau max. Okay, so then you get this equation. So what happened now? We get a relationship for the shear stress. So previously we found that shear strain is linearly distributed in the cross section, and now because of the Hooke's law, we can see that shear stress also linearly distributed. Right. So that is what here it says, the shearing stress varies linearly with radial position in the section. So at the center, now circular cross section, at the center shear stress is 0, and at the outer surface here shear stress is maximum, tau max. Okay, and this is for a circle with a radius c. Okay, and if I want to find out the shear stress at one point here, let's say a very small area, and if I define the radius to that point as rho, so at that point shear stress is, we can write as a generic shear stress tau, and this is equal to rho over c times tau max. Okay, right, so that is about the shear stress. In fact, this shear stress is developed because of the torque applied, right? So if I apply a torque in this direction, external torque T, right, it creates an internal resistive torque T. So the distribution of the shear strain created by this torque is given by this rectangular or triangular distribution, right? Now we know the shear stress at this small point in here. Let me take this point as dA, area as dA, very small point dA. So if I want to find out the torque resisted or resistive torque at that point, can you find out the resistive torque at that point? So I can say that for finding the resistive torque at that point, first I need to know the force at that point, that is dF, small force, shear force applied on that small element, that will be equal to tau times dA. You understand what I'm doing here now? I take the shear stress at the area dA and multiply it by dA. Then I get the force on that small area, tau into dA. So now if I want to find out dt, that is the small torque, resistive torque, right, created by that small area, that is be equal to rho times dF, rho times dF, that means tau into dA, right? So dt is a moment, right? Twisting moment. So how to find out the twisting moment? You have to multiply the force by the radial distance or perpendicular distance, that is rho. So if I want to find out the T that I marked in red color inside, that is the resistive torque, right? That T should be equal to summation of or integration of dt over the whole area. Okay, so that means this should be equal to over the whole area rho into shear stress into dA. Okay, this is T. Now if I identify this like this, and can you see that same equation written here? That is how that equation is written. So here T is the internal torque, internal resistive torque. Okay, so internal resistive torque now can be expressed by this equation. So if I replace this tau with this equation here, this equation in tau, then you get this part. Okay, there integration rho square dA is actually a very important quantity, and it tells me how much the cross-sectional area, this circular section, resists the deformation, or it tells me the inertia for the moment applied, how the moment is resisted. So that is called the polar moment of inertia. So this J is polar moment of inertia. Maybe you have learned about polar moment of inertia in your previous courses, right? So it is basically the resistance to deformation, right, by the cross-sectional area. So this J depends on the geometry. Now we are now studying a circular cross-section, right? For circular cross-section, J, that is the polar moment of inertia, you can express by this equation. This is a standard equation. Again, you might have learned this one before. No need to remember, right? Just take it as it is. This is how we quantify the polar moment of inertia of a circular cross-section. Here C is the radius, and it is given in meters to the power 4. Okay, and if you take a different cross-sectional area, the polar moment of inertia is different. For example, for hollow circular section, polar moment of inertia is given by this equation. Okay, right. Now, by simplifying all this equation, you get this relationship, right? Tau max is equal to Tc over J. So which is very important equation now, because when it comes to designing something, always we need to find out the maximum stresses generated, internal stresses generated, right? So now we know that once we apply a twisting moment torque, it creates a shear stress, and that shear stress is the highest at the outer surface. At the center of the circular bar, shear stress is 0. So therefore, when it comes to designing, you need to find out or quantify the maximum shear stress. Now, we can quantify the maximum shear stress in terms of applied torque T, right? And the geometric details, that is the maximum radius, because maximum shear stress happen at the maximum radius, and the J also geometrical property, polar moment of inertia. So if you know the polar moment of inertia for that given cross section, and if you know the maximum radius of the member, knowing the external torque, we should be able to find out the, okay, sorry, not the external torque, knowing the internal torque, we should be able to find out the shear stress. So that reminds me a very good important thing, that is to tell you that this T is the internal resistive torque. Okay, so maybe I will mark it in red color. Okay, the same T I marked in here, internal torque. Okay, so if you want to find out the stress at any other point on the radial at any radial position other than outer surface, then we can use this equation. Okay, so I can say that this is the generic equation. Okay, and this equation is called the elastic torsion formula. Very important equation. So we have learned how to quantify the shear stress, knowing the internal torque. So if you know the internal torque, now you can find out the maximum shear stress. Okay, and this is valid only for a section which will remain the same even after deformation. So this is valid for solid circular section, hollow circular sections. And if you use any other different section, then you need to find out the polar moment of inertia for that section. Okay, so the next slide shows you the polar moment of inertia for different cross sections. So the first one in here, this one is for the circular section, but you can see it is given in terms of D. And if I know the radius as C, then J is half, so I can say pi by 2 to the C to the power 4. in terms of diameter, it is pi by 32 to the power into d to the power 4. Okay. And for other sections, you can see using characteristic dimensions of the section, you can find out the polar moment of inertia. So whenever you are using different other sections, you need to find out the right equation to find out polar moment of inertia. Right, now I think we have some knowledge or information how to find out or quantify shear stress resulting from torque. So let's try to apply that and see how to solve problems. So the first one is completely done for you with all the steps, but I would like to go through it with you and show you how to complete the question. So what it says, a hollow cylindrical steel shaft is 1.5 meter long. So this is the length, right? Length L, 1.5 meters, and has inner and outer diameters respectively equal to 40 and 60 millimeters. So it's a hollow circular bar, so we know the inner and outer diameters. What is the largest torque that can be applied to the shaft if the shearing stress is not to exceed 120 megapascal? So this shearing stress is the maximum, right? So we know that maximum shear stress is 120 megapascal. Okay. And if there is a circular cross section, I'm going to draw my cross section, a bigger diagram, so that I can draw the stress distribution. So if I take a one section here, and then I know that once I apply this torque T, the shear stress maximum going to be in the outer surface here, tau max. Okay, and then it linearly vary from the maximum to the minimum. So here in the middle, there's no material. Therefore, the minimum shear stress going to be here. This is tau minimum. So in between, the variation is linear. So the arrow shows you the size of the shear stress, right? So now we need to make sure that tau max is less than 120. And at that time, what is this value T? That is the first part. B, what is the corresponding minimum value of the shearing stress in the shaft? So that means we need to find out tau minimum. Okay, we need to find out this T when tau max is 120 and tau minimum at that torque. So let's see how to work it out. So going to use my equation here that we just derived. So this is the equation. Okay, tau max is equal to Tc over J. I'll just write it here. Tau max is equal to Tc over J. And then since we need to find out the maximum torque when the tau max is equal to 120, I just solve the problem for T. Right? And here tau max is given, and C we already know because it is 60 millimeter, the radius diameter is 60 millimeters. Therefore, C is 30 millimeters, and only unknown here is the J. And we know that it's a hollow circular section. Therefore, for hollow circular section, polar moment of inertia is given by this equation. Okay, C2, that is the maximum radius is 30 millimeters, minimum radius is 20 millimeters. Therefore, we can get this value for polar moment of inertia. And C, the units is meters to the power 4. Okay, so now it is very simple. By substituting the value of J in the previous equation, we can calculate the maximum torque we can apply. It is 4.08 kilonewton. Knowing that, next we need to find out the minimum shear stress. So we know now the distribution of the shear stress, right? So how to find out the tau mean? So you can easily find that one by looking at the triangles. We can use similar triangles to find out tau max. So I just draw this distribution. This is tau mean, and this one is tau max. Okay. And this length here is C1. This one here is C2, maximum radius. Okay. So now by looking at the two triangles, small one and the big one, we can write tau mean over tau max is equal to C1 over C2. Okay, so using this equation, okay, we can find out tau mean. Okay, that is how we find out the shear stresses or the maximum torque that we can apply so that the shear stress will not exceed by a certain limit. Okay, so now let's push our knowledge a little bit further. Okay, challenge ourselves by doing this next exercise. And this exercise, there are a lot of gaps. Okay, I have not completed it. So you need to write down together with me. And as you write, don't simply copy, try to understand. And if you have any difficulty in understanding, let me know so that I can explain again. Right. So what it says, the pipe shown in figure below has an inner diameter of 80 millimeter and outer diameter of 100 millimeters. Inner diameter 80, outer diameter 100 millimeters. So it is again a hollow circular section. So therefore, just try to visualize always, right? So we have this inner and outer diameter, and the material is shown in here by the hatched lines. Diameter of the inner side is given, inner circle is 80, and the outer diameter is 100 millimeters. Okay, if its end is tightened against the support A using a torque wrench at B, so this cross arm is a wrench, and you can see a person is trying to rotate it. Therefore, AB, which is fixed at A, now going to twist. Right? So it has to resist this twisting moment. Determine the shear stress developed in the material at the inner and outer walls. So we need to find out the shear stress distribution, inner and outer walls. That means this maximum and the minimum value. So tau mean here and tau max. So that is what we need to find out. The central portion of the pipe, when the 80 Newton forces are applied to the wrench. So you can see 80 Newton force is applied at this point and this point here, and they are 300 millimeters and 200 millimeters from point B. Okay, right. So if you want to find out the shear stress, now we know that we have to use this equation. And there, what is this T here? It is the internal torque, right? Internal torque. So that is what we need to find out here. Internal torque. Now we need to find out the shear stress and shear stress distribution at the midsection, that is at C here. So that means we need to find out the torque at internal torque at that section. So if you can find out that internal torque at section C, the rest is given, right? Geometric details C and J are easily find out. We can find out easily. So only thing here is to find out this T. So if you want to find out the internal torque at C, then we need to cut this member at C and take the cut portion out and draw a free body diagram. And using free body diagram, you should be able to find out the internal torque. So before I explain how to find out that internal torque, I just want to introduce you a sign convention here. I mentioned that torque is a vector. Vector has a direction, right? So how to find out the vector direction? Maybe some of you already learned this one before, right? So we use the right hand rule. So if you can remember in previous section under axial loading, we always mark moment in anti-clockwise direction as positive, right? There, the torque that we talk, or the moment that we talk about in axial loading topic, they are just moments. They are not twisting moments. They are not torques, right? But under torsion, this topic, we are talking about again moments, but they are twisting moments. So for twisting moments, we need to define our own way or different way of identifying the direction, positive directions, right? So that is why we use this sign convention, right hand rule. How to find out the direction of the torque? You simply curl your four fingers in the direction of the torque applied, and then look at where your thumb is pointing. So now here, if you look at the bottom diagram, your thumb is pointing this way, right? And when you curl it in this direction, so this is the direction of the torque, right? The circular direction of the torque, and then the vector direction of the torque is in the thumb direction, okay, in this direction. Okay, the rest also explaining the same. I hope that you got the right hand rule, and whenever we are writing our equation of equilibriums, we need to know the direction, right? So if you don't know the direction of the torque, you will get a wrong answer. Therefore, always use this right hand rule. Okay, so now move to that question. So this is the free body diagram drawn, right? F, B, D, and this is the point B, and this is point C. Okay, so 80 Newton, two forces are marked here. I taken out the hands, right? So the position of the load application is 300 millimeters and 200 millimeters away from B. And I have marked the XYZ coordinate system, and this is the positive Y direction. This is positive X, positive C. Better you mark those arrows. Okay, right. So now I have just marked the internal torque T in direction shown. So now this is the internal torque. At C. Internal torque at C is T. Right. So we need to find out this T. So therefore we need to write equation of equilibrium for this free body diagram. So we need to first identify the positive direction, right? And then write the moment balance for this whole free body diagram. Okay, so I'm going to take moment around y-axis because our internal torque T is in y-axis. It's applied about y-axis, right? So we'll mark the positive direction in y direction this way. Right? this is positive y direction, and take moment in that direction and add them all together, it should be equal to 0, right? So now let's write this equation together. Then you understand how to write the moment of equation of equilibrium for this kind of situation where there are only torques. Okay, the first thing, we'll take the internal torque T. So tell me whether internal torque T is in the positive direction of y or negative direction of y. I would like to hear answer from you using your right hand rule. So what you have to do, take your right hand and curl your fingers in the direction of the torque. Then see where the thumb is pointing. If the thumb is pointing in the positive y direction, that torque is positive. But if it is opposite, that torque is negative. Okay. Therefore, now internal torque T, is it positive or negative? My question is for you. Can you tell me, somebody, what is the direction? Is it negative? The torque is negative or positive? Internal torque T. Negative. Thank you very much. You understand what I'm talking about, right? So therefore, it is negative T. Now we'll take the force 80 Newton in here. So that force 8 Newton going to create a moment around y. Okay, so now tell me whether it will create a positive moment or negative moment about y. So the moment it creates about y, right? So again, you just mark the direction of the torque, or you can curl your fingers in the direction of the torque. Then you can look at your thumb where it points to positive y direction or negative y direction. Again, tell me the sign, negative or positive. So here it will create a torque in this direction, right? So you curl your fingers in that direction, it is positive, right? So therefore it is positive. What is the size of the torque? Force into the distance. Okay, 80 into the distance is 200 millimeters. Therefore it is 0.2 meters. Right, and then take the second one, 8 Newton here. So again, is it a positive or negative moment? It creates a moment around y again, right? So it's negative or positive? Now it is easy, right? So it is positive. So positive 80. Now the distance is 300 millimeters, 0.3. Any other forces or any other moments? None, right? Therefore, this is equal to 0. Now you know how to write the equation of equilibrium? You can, right? Right. So once you simplify this equation, you get this answer. The internal torque at point C is 40 Newton meter, right? And the direction I marked is correct, right? It's a positive direct. It is in the right direction. So you don't, you just take it as it is, and then we are going to find out the stress, shear stress. Tau is equal to T rho over J, or you can say, if you use the maximum, want to find out tau max is equal to T times C over J. So here we already found T, and then C is a non-value, and the next one is J. How to find out J? This is, we have already marked the cross-sectional area. Okay, so it is hollow circular. For hollow circular section, the J is given as this equation. Okay, already it is written here, right? So C2 is the outer radius. So it is pi by 2. Outer radius is 100 millimeters, that is 0.05. Radius to the power 4 minus inner radius, I can't remember now, 80. Diameter is 80. Therefore, radius is 0.04 to the power 4. So after simplifying, you get this answer. Okay. Now we need to find out first the maximum or the stress in the outer surface. Okay. That means when rho is equal to CO is equal to outer radius, is outer radius. So I use this equation. Okay. So this is the outer shear stress. So T is 40 Newton meter and CO is 0.05 and divided by J, already found, 5.796 to the power 10 to the power minus 6. Okay, you get this answer. So this is the shear stress at the outer surface. And next we need to find out shear stress in the inner surface. So how to do that? The rho, the radius is the inner radius. Same equation now, right? And there you substitute all the values. T is 40 and the CI is 0.04 and the J is the same or different? Same cross section, right? For the same cross section, J is the same. So therefore the same cross section, J, we just calculated 796 10 to the power minus 6. Then you get this answer. Okay. Right. So we have learned one equation, that is the shear stress equation. Once the torque is applied, once we know how to find out the internal torque, we can find out shear stress at any given cross section, knowing the geometric details. Okay, right. So now what we'll have learned, actually, if you take a cross section which is perpendicular to the major axis. So this cross section here, you can see that this cross section is perpendicular to the major axis. So in that axis or that cross section, what you can see, only a shear stress, no other stresses, only shear stress. So what about other sections? If I cut this member in an angle, do we see different other stresses? In fact, answer is yes. So for your information, on a perpendicular cross section to the major axis, we find shear stress only. But in other angle, let's say if we cut this member in a 45-degree angle or any angle like this, on this surface, you find that not only shear stress, but normal stresses too. That normal stress can be shear, the tensile stress or compressive stress. So this is very interesting because depending on the properties of the material, some materials are categorized as ductile materials, some others are categorized as brittle, right? So brittle materials are hard and they are very weak in supporting tensile forces. They can support high shear stresses, but tensile forces, tensile stresses, they easily break, like glass. So if you try to bend it, it will break easily, right? But if you try to shear, it's very hard to shear, or the the shearing across its cross section is very hard, but bending will create a normal stress, and then it will break easily, right? So this is something very interesting when it comes to torsional loads. The failure behavior going to be different depending on the material properties. Ductile materials like mild steel, if I take mild steel, they shows, or they normally fail because of the maximum shear stress. If the maximum shear stress reaches to yield shear stress, they fail. So we know now that maximum shear stress is going to happen at a cross section perpendicular to the major axis. Therefore, mild steel is going to break across the major axis like this, if you apply a torque like this. But if you apply a similar torque to a material like cast iron, you will see a failure like this. It is going to fail in an angle like this. The reason, because in this angle, other than the shear stress, now here we find only shear stresses, so all the stresses are on the plane. But here they are going to be tensile forces like that. Because of the tensile force, it breaks like this, right? So you will observe this one, or you are going to experience this one, because we are going to do a lab test later. You have lab classes. In the lab classes, we will give you two different materials, cast iron and mild steel, and subjected to torsion test. So then you can see how they fail. So this failure is because of the way the stresses are generated in the cross section. Okay, so to give you a little bit more information, now this can be a bit complicated for some of you. Some of you might understand it. Okay, so just to complete the discussion, let me show you how the stresses are developed. Okay, so maybe I will go to the next slide and show you how the stresses are developed or forces are developed. Okay, so this is a circular member and subjected to torque T. And now if I take, say, front view like this, it's a rectangular shape, and then I'm going, if I cut this member across here like this, and then draw the same rectangle, or not the rectangle, square here, right? This square represent only a point on the cut surface, a small point. But since I cannot mark all the stresses on a point, I'm going to magnify it into a bigger square. This is in 2 dimension, but in fact I'm now referring to a 3-dimension cube. So if I draw the cube in a bigger scale, it would be like this. Actually, this is representing a small point on the surface, right, like this. And this cross section of one face here, we can take it as A0, original cross section. And this is a small cube, okay, small cube representing a point on the shaft. Okay, so now we know that on this cube, there are going to be only a shear force or shear stress like this, right, all around. To make it balance, it should be like this. So what if I cut this member in a 45-degree angle like this? So that means I'm going to cut the cube in this angle. And then I'm going to take this part out, the cut bottom half and draw it in here. So what I have drawn here, that bottom triangle in 2 dimension, but it is actually 3-dimension cube. So if you cut the cube like this and take the top half out and the bottom half I have drawn in here. Okay, so on this surface there's a shear stress. I mark it as tau. Since it is in the outer surface, it should be tau max. Okay, and these are tau max. And since the cross-sectional area is AO, right, and the force along that surface I can write as tau max AO. So this is the force, shear force, right? Similarly, the bottom surface BC also tau max A naught. And those are the internal forces generated, or shear forces generated, right? And then from the for the equilibrium, there should be internal force, and let me mark the internal force perpendicular to that cross section DC, and also there can be a shear force. I mark that shear force as L. This is Fs, shear force along the surface. We don't know what is the size of that, and there can be a normal force, and also we don't know what is the size of that. But by writing the equation of equilibrium for this small element, we should be able to find out F and Fs. Okay. So what I'm going to do now, I'm going to write equation of equilibrium for the cube for the small, for the element. That means I'm going to take moment balance in this direction. Summation of all the forces in that direction is equal to 0. So in that direction now, there's a force F, okay, positive direction, and then tau max AO should have a component in that direction, right? So since the angle is 45, it is in the negative direction, tau max into AO into cosine 45. Okay, so that is from the first one. And the second side, also the same magnitude, same direction. Therefore, I can write this one as 2 times tau max AO into cosine 45 should be equal to 0, right? So that means this force on the 45-degree angle surface, normal force F, should be equal to 2 times tau max AO into cosine 45, means 1 over square root 2. Okay, so I can further simplify this one further. Square root 2 cut off, and then it becomes square root 2 times tau max times AO. So that means there's a normal force on a 45-degree angle plane, and it has a positive value. That means there's a normal force. How about the shear force Fs? So if you want to find out the size of the shear force Fs, we can take the, I forgot to put positive sign here, force balance in that direction. Summation of all the forces should be equal to 0. Then you get Fs in that direction, and then get opposite direction from this one, negative tau max into AO, again cosine 45. Okay, and the second one, this force is in the same direction, that is positive tau max A naught cosine 45 equal to 0. So these two cancels off, right? That means Fs equal to 0. That means just there's no shear force. This is interesting because on a perpendicular cross section to the major axis, there's only shear force, no normal forces. Okay, but once you cut this member in 45-degree angle, you find that on that surface, there's a normal force. The size of the normal force is this much, and along the surface, no shear force. Okay, so now we can see the reason why brittle members like cast iron fail in 45-degree angle. So this angle here, let me see, this angle here is in fact 45 degrees, because at 45-degree angle on that plane, normal force is the maximum. So the failure, cast iron, like brittle material like cast iron, cannot support very high tensile forces. We apply torque, so torque create internally a tensile force normal to the cross section, 45-degree angle cross section. So as a result, failure happened due to tensile as a tensile failure. So this is a shear failure. I can say shear failure. Okay, but this one is a tensile failure. Okay, so more details you can study during the lab experiments, and you should be able to explain why different materials fails in a different way using this knowledge now. Okay. Okay, so in fact, if you don't understand what I explained here, no need to worry too much. Later in the your lab test, you can study it a bit more, right? And no testing is done, or you don't need to do any calculation based on these things. Okay, right? So it's 5 already. So let's have a short break. Okay, after that, I'll continue with the same next slide. So let's start at 10 past 5. Okay, right. So if you have any questions based on what we have learned so far, you can ask those questions now. Okay, hope you are back. Right. So during the break, I have just looked at the attendance mark on the Moodle course site and the number of students present at this moment. Right. There are only 48 online at the moment, but 60 of you have already marked the attendance. Okay. So don't think that you are going to get knowledge by marking attendance. It is cheating yourself. Okay. So the attendance is useless if you are not really coming to lesson. So I can download the current attendance list, okay, from the MS Teams. So I will keep it as a record, not the one available online in the Moodle course site, because there is not reflecting the reality. Okay. So if when there are border cases, when it comes to pass and fail, we will look at that kind of attendance. Those who cheat always get the punishment. Okay. This is unprofessional and also not good for a professional engineer. So we are training engineers here. Okay. So I'm telling this one as a record. Those who are going to listen to this recording later, who are not present now, yeah, they will realize the consequence. Okay. Okay. So those who are present, it is not for you guys. Right. So let's move on. Another exercise. And this one is challenging you a little bit further. Once you do this question, I guess that you have a full understanding on how to use the stress calculation equation, right, that we have just learned. So here the torque application is quite complicated, and you find this kind of applications in many mechanical systems. Okay, so let's read the question first and try to understand it, and then work out the question together. Again, there are a lot of gaps to fill up, so you need to write them down, and as you do the writing, you train your brain, right? So do it. Okay, so what it says, shaft BC is hollow. So there's long shaft, BC portion is hollow with inner and outer diameters 90 millimeter and 120 millimeter. Now this is for cross section BC. Okay, if you take a cross section at between B and C, it's a hollow shaft. Shaft AB and CD are solid of diameter D. Yeah, diameter D here, it is not given. For the loading shown, determine A, the minimum and maximum shearing stress on the cross section of shaft BC. Now it is very similar to a question that we have done before, right? So we know that is a hollow circular shaft. We have to find out the outer surface shear stress and inner surface shear stress. That is the maximum and minimum. Part B, the required diameter D of the shaft AB and CD if the allowable shearing stress in these shafts is 65 megapascal. So when you read this and you understand this is the maximum allowable, or we say maximum, okay, maximum shear stress should not exceed 65 megapascal. That means it's a solid shaft. In a solid shaft, maximum shear stress is going to happen in the outer surface. Therefore, we should be able to find out that maximum shear stress using these equations. Okay, same equation, only difference is first one provides the maximum shear stress, and the second one shear stress at any radial position. Okay, So now, if you want to find out the shear stress between, first, let's say between AB or CD, by looking at the way the loads are applied, the torques are applied, you can see TD is 6 kilonewton meter, TA is 6 kilonewton meter, right? And from A to B and D to C, no other external loads. Therefore, CD and AB internal torque going to be the same. Do you understand what I'm saying? So inside AB and CD, they are going to be same internal torque. But in BC, cross section BC, internal torque should be different. Okay, right. So let's try to find out the internal torque first, because we know that this T here is the internal torque. Okay, so for that, what we have to do, we have to first cut the member between A and B, any point. Let's say we cut from here and take out the cut portion and draw a freeboard diagram. Once you draw the freeboard diagram, you see the internal torque and then you can quantify that. Same thing we can do for the section BC. Cut the member from B to C and again draw a freeboard diagram and you can find out TAB, that is the internal torque. So you go to the next slide. It shows you a partially completed solution. So we'll work together and complete the solution. Right. So now here in this diagram, first one, what you see is the freeboard diagram for the cut portion from A to B. There TA is the externally applied torque and TAB here, maybe you mark in different color to show that this is the internal torque, right? Internal torque is the internal torque. So this is what we need to find out if you want to find out the torque inside, or the resistive torque and shear stress between A and B, right? So now we need to first define our directions, right, properly. Maybe we mark the arrow to show the x direction, positive x direction here. So we'll take moment in the positive x direction, this direction, and add them all together should be equal to 0. So see how the equation is written, and TA is a positive moment. You can see why, right? You curl your fingers in the TA direction, then your thumb will point positive x direction. Therefore, it is positive. This is positive. And TAB, when you curl your fingers in the TAB direction, your thumb points in the negative x direction. Therefore, it is negative. So finally, TAB is this one. Okay. In fact, by observation, you can write that, but I want you to understand how it has been written here. Now, with that knowledge, you should be able to now do the find out the internal torque between B and C by using the second freeboard diagram. It is a portion cut between B and C. There again, the TBC is the internal torque. TBC, internal torque, right? Internal torque. Right. So now again, can we write the moment balance here? It is not given to you, so you have to write it by yourself and mark the positive x direction for in the diagram, and then we will take the moment in positive x direction. And all the forces at moments add together should be equal to 0. So again, start with TBC. Is it positive or negative? TBC in the negative direction, right? Therefore, it is negative TBC. And TB in the positive direction. Therefore, it is positive 14. Okay. And how about the TA? The same direction, right? So therefore, positive 6. So that is how I got this TBC equals 20 kilonewton meter. Okay, now we have the internal torques between BC and AB, and it is what we found as TAB is equal to TCD as well, because internal torques are the same. Okay, so between B and C, cross section is hollow cylindrical, hollow circular section, and now we are going to use our formula for torsion formula, and there we already found T to find out the maximum shear stress, and then C already given. The only thing that we need to find out J. So that is what I'm doing here, finding J. So once you know the polar moment of inertia, now it is matter of just simply substituting the numbers. T is equal to TBC, C maximum is C2, that is 45 millimeters, J we already found, right? So let's write all the values. This TBC is 20, right? 20 kilonewton meter. So therefore you need to multiply it by 10 to the power 3. And C2 is 60 millimeters, that is 0.06 divided by J. J is 13.92 into 10 to the minus 6. So you should be able to do the calculation and get the answer. The answer is here, it is given. Tau max is 86.2 to the power 10 power 6 Pascal. So this is what I got. Okay. And next, I need to find out the minimum, right? Minimum shear stress, which is going to happen in the inner surface. And there, again, what you have to do, you just draw your triangle here, right? Similar triangles. By considering the similar triangles, you should be able to find that value. So this is tau min, and this one is tau max. Okay, so this distance here is C1, and this distance here is C2. Okay, and from the similar triangles, you get this one, and from, since we already know tau max, C1 and C2, you can find out tau min. So the answer is here. I hope that you can complete that part. Okay, right. And next, we need to find out the allowable, sorry, not the allowable shear stress, right? The diameter, that means this diameter here, D. What is it? So what is given is tau max. Tau max is given as 65 megapascal. It cannot exceed more than that. Okay. So now we are going to start with our equation. Tau max is equal to TC over J. All right. And here our target is to find out T, and J is pi by 2 times e to the power 4. So if I simplify this one, I get tau max is equal to 2 times T divided by 5 C to the power 3. Correct? Okay, so that means 65 into 10 to the power 6 is equal to 2 times, actually this is TAB, right? TAB. TAB, previously we found the value, it is 6 kilonewton meter. 6 into 10 to the power 3 divided by 5 into C to the power 3. So only unknown is C. So you do the calculation, I got this answer. C is equal to 38.9 into 10 to the power minus 3 meters. So then I can find out D. Okay, so that is how we solve that problem. The thing that we have learned is how to find out internal torque using equation of equilibrium, and also using the right direction, right? So you have to use your right hand rule to find out the direction of the torque. So if you miss it on that one, if you get a wrong direction, if you mix up with that, you will get wrong answers. So practice it more and learn. If you don't understand, let me know, I can explain again. Okay, so now that is about the shear stress resulting from applied torque. Now I would like to introduce you another concept, that is how to estimate angle of twist. Okay, so again, in the elastic range, how to estimate the angle of twist using known values like the applied torque, geometric details, and material properties. So for that, I would like to show you the derivation that I have done at the beginning. So I go to next slide first, and there I hope that you can remember this initial calculation, and then by looking at the displacement A prime, I have written two equations and equate them, and then I got this equation, right? And later, using simple manipulation, I found that gamma max is equal to C of pi over L, and then we got this relationship where it says that shear strain is linearly vary from center to the outer surface. Maximum shear strain is at the outer surface, right? So now I go back here, and you can remember this equation now. Okay, so this is gamma max, maximum shear strain is equal to C times phi divided by L. So let me mark this one as equation number 1. Right. And then from the Hooke's law, right, previously we did in the elastic region, we can use Hooke's law. Therefore, we know that shear stress is equal to G times shear strain, gamma. And if we want to find out tau max, maximum shear stress should be equal to G times maximum shear strain, right? Okay, so now I use this equation to write an equation for gamma max. So this gamma max here is coming from the Hooke's law. Now previously, we learned the torsion formula. Tau max is equal to Tc over J, which is given in this box here. And here, in place of tau max, now I can write Tc over J. So let me take this Tc over J and replace tau max, this tau max. Then I get gamma max is equal to TC over JG. My target is to find out an equation to measure shear strain or the angle of twist using known values. Okay, so now I got another equation for gamma max, two equations. So one is equal to 2. So by equating those two, I can derive this equation. You see, C will cancel off, right? So only remaining quantities are phi over L equals T over JG. So from that, I can get this equation. So this is the equation for angle of twist. And there, you can see applied load torque is in the equation, which is normally known. Sorry. Then angle phi depends on the length of the shaft L, and also it's going to depend on the geometric cross-sectional geometry as well. So that is the polar moment of inertia. So inertia depends on the cross-sectional shape, and also the angle of angle of twist going to depend on the material property. Here the material property is the rigidity modulus. Now if you can remember, in the axial load case, we calculated equation for axial deformation or elongation or contraction. Can you remember the equation? It is delta axial elongation. Delta is equal to PL over AE. Can you remember that equation? And there I said that the elongation depends on applied force P and the geometric details of the member, length and the cross-sectional area, and also the material property E. Now, can you see some relationship between this delta and angle of twist phi? Two equations are very similar, right? So you can see the load, in this case T, torque, and the axial load case is the axial load, and the length of the member and the geometric detail, cross-sectional details come into the equation as A cross-section in the delta equation, and here in angle of twist calculation, it is the polar moment of inertia. Okay, and the material property comes using the Young's modulus and the shear modulus. So they are very similar. And here another important thing, this equation phi is equal to TL over JG provide us the angle of twist in radians. Okay, and this equation valid only if, because this equation is derived for this kind of member, right? So this is valid only if the internal torque remains the same along the length. So here you can see there's only one torque T from, let's say this one is A, this is B. From A to B, same internal torque and the same material, therefore G is constant. Same cross section, therefore J is constant, right? So this equation valid only for this kind of member. So what if we have a compound member shown in here, second diagram? There the cross-sectional areas are different and internal torques are different at different places. Therefore, this equation cannot be used directly to find out the total angle of twist in this member. And another important thing I want to mention here, angle of twist phi given in this equation is the angle of twist at point P with respect to A. Okay, right. So now in the second diagram, diagram below, compound member, if you want to find out the total angle of twist of the member with at point A with respect to B, so then we need to apply this equation for different sections where internal torque is the same, cross-sectional area is the same, material properties is the same. Okay, so therefore, if you by observation you can find out A to C, this member has the same parameters. So therefore, one portion C to D, another portion where everything's are constant, and D to E is another one, and E to P another one. Right. So there are 4 portions in here. If you want to find out the total angle of twist at A with respect to B, this is how I write it. Right. Just learn the convention. Phi of A with respect to B is equal to phi of portion 1, phi of A with respect to C. That is the angle of twist of portion 1 with respect to C, plus phi of C with respect to D, plus phi of D with respect to E, plus phi of E with respect to B. So this is how we find out the total angle of twist. So a compact version of the same equation is this. Okay, it is very similar to what we have done in axial load case, right? There again, if there's a compound member, we identify several portions of that compound member where we can apply this equation. Okay, and then we use principle of superposition to find out the total elongation or total contraction. Okay, right. So with that knowledge, I hope that now you can apply this equation to find out angle of twist resulting from applied torques. And remember again here, T torque that we are talking about is not the external torque, but the internal torque. Okay. So let's work out this question. So what it says is the same question actually, but different thing that we need to find out. We have done a similar question before. So it says a hollow cylindrical steel shaft is 1.5 meters long. So length is 1.5 and has inner and outer diameters respectively equal to 40 and 60 millimeters. What torque should be applied to the end of the shaft to produce a twist of 2 degrees? So this is the angle of twist, right? Is equal to 2 degrees. It is given in degrees, but remember previously I mentioned that angle of twist is measured in radians. In the equation, we need to substitute that in radians. Okay, right. G is given as 77 gigapascal. Right. So what we need to find out the torque that generates angle of twist of or create angle of twist of 2 degrees. So straight away we are going to use this equation, our angle of twist equation. Their length is given, G is given. Since we know the cross-sectional details, geometric details, we can find out J, right? Phi is given. So then we can find out T. In fact, we don't know J directly, so but we can find the J first. So that is what I need to do first, right? Find out unknown quantities. So here I'm going to start with my equation for angle of twist. Since I need to find out torque, so I just solve it for torque, and then G is given, L is given, phi is given but in degrees. So I converted phi into radians. So you see, I multiplied by 2 pi and divided by 360 and then convert into radians. So I got the answer in radians. And for J, since it is a hollow circular section, in fact, we have found the J before, right? So if you want to do it again, what you need to do, you just write this equation c2 to the power 4 minus c1 to the power 4. So from that, we get this equation, this answer. Okay, right. So now it's a matter of substituting the numbers. And once you substitute the right numbers in right units, remember, always use the right units, then you get the answer in Newton meters. So the kilonewton meter is this. Okay, so that is a concept application. All the steps are given. Now let's challenge ourselves by doing a bit complicated question. Okay, what it says, the horizontal shaft AD is attached to a fixed base at D and is subjected to the torques shown. Okay, there are two torques that is fixed at section D. A 44 millimeter diameter hole has been drilled into the portion CD. So it is talking about this part. It is hollow, inside hollow. Okay, portion CD of the shaft. Knowing that the entire shaft is made of steel, for which G is 77 kilopascal, determine the angle of twist at end A. So this is a compound member, right? So there are several sections with different geometrical details and different internal torques. So therefore, if you want to find out angle of twist at end A, it should be with respect to D, right? Because D is fixed. So we need to write this equation. So if I write you a long equation, it is phi of A with respect to D should be equal to, first identify the portions where, or sections of the member where things are constant, geometric details are constant, and the material properties are constant. A to B is one portion, right? A to B. And B to C, again, is a solid shaft. No, the diameter is 60 millimeters, and internal torques are different. Therefore, we can mark it as 2. And C to D, inner part is hollow. Therefore, it's a hollow circular member. So this is the third portion. There are 3 portions here. So phi AD is equal to phi A with respect to B plus phi B with respect to C plus phi C with respect to D. Right. So therefore, now we need to find out phi AB, phi BC, and phi CD. We need to know the internal torques from A to B, B to C, and C to D, and also the polar moment of inertia. Okay. Right. See how all the partially completed solution is given in the next slide, and let's work out together to find out the internal torques first. So to find out the internal torque between A and B, you need to cut this member any point between A and B and draw a Freiburg diagram. So what is drawn in here is that Freiburg diagram, FBD, FBD for A to B, any point between A to B before B, just before B, okay? And again, I mark my internal torque here, okay, TAB. So if you mark your positive direction of X like this and take the moment balance in that direction as a positive direction. So can you write the equation now? 250 creates positive or negative moment? Positive moment, right? Or negative. 250 creates a negative moment. Am I right? So therefore it's negative 250, and TAB going to create a positive moment. So plus TAB should be equal to 0. So that is how this TAB is calculated. Okay, and then for B to C, we need to cut the member between B to C, somewhere here maybe. Okay, and draw a fiber diagram for that cut portion, right hand portion. So that is what I have drawn here, FBD, and the internal torque between B and C is marked as TBC. Again, we are going to write the force moment balance and taking positive x direction in this direction. This is the positive direction. Can you write the equation now? So it's, in fact, mx should be equal to 0, right? Yeah. Right. So 250 going to create a negative moment. So negative 250, and 2000 also create a negative moment, negative 2000, and TBC create a positive moment, positive TBC. That's all should be equal to 0. So once you simplify, you get this answer. And next, we need to find out the internal moment between C and D, So for that, again, you need to cut this member between C and D and draw a freeboard diagram. But by observation, you can see that from C to D, there are no other extra torques applied. Therefore, internal torque is the same from B to D, whole section, B to C and C to D, the internal torque is the same. That's what written in here. Since no torque is applied at C, up to C, or after C, TCD is equal to TBC. Okay, same value. Okay, now we are going to use this equation and apply this equation for portion by portion and add them together to find out the total angle of twist at point A. So to complete the equation, I need moment of inertia between each section, or for each section. So AB is a solid circular section like this, right? Therefore, I use this equation, and BC also solid circular, same equation, right? Same equation, and C to D is a hollow circular section. See, hollow circular section, and then I use this equation and calculated the moment of inertia, hollow moment of inertia is easy. Now you should know how to do that. And now it's a matter of adding them all together, right? I mean the angle of twist with respect to a given point. So shall we write it? To complete the calculation, maybe I'll write the whole thing. TAB into LAB over JAB times G, right? And then add the second portion, CBC LBC over JBC times G, plus third portion TCD LCD divided by JCD times G. Okay, now you should be able to substitute all the numbers. Okay, I leave that part for you and write the answer directly here. I got the answer as 0.0403 radians. Okay, this is my answer. So you do the calculation and see whether you can get the same answer. And once you convert this answer into degrees, this is the final answer. And see whether you can get this answer as well. So I leave that part for you. Okay. So any questions? Okay. So today we have learned new few new concepts to study or to analyze members subjected to twisting moments. So the first thing that we learn is that once we apply a torque onto a circular member, uh, uh, it's going to create a strain in the cross section. That strain is linearly distributed. Maximum shear strain is in the outer surface of the member. So the strain distribution is linear. Right? So it varies from the maximum value at the outer surface, and then at the center it is 0. So this is the gamma max. So this is the variation. And then using Hooke's law, we have derived the torsion formula. We call elastic torsion formula, which is very important formula. Now we can find out the shear stress variation, maximum shear stress as well in a member subjected to twisting moment. And there I clearly mentioned that the torque here is the internal torque, which is not the external torque. Okay, right. And then lastly, we learn how to find out the angle of twist using known values. So angle of twist is a function of the applied torque T and also the length of the member and the material properties too. Okay, so there this equation is valid only for a member where the cross section remains the same material properties, internal torque is the same. But for a compound member, we need to find out the values for each section and add them together to get the total deformation, total angle of twist. So that is what we have learned so far. So today we have learned two important equations. So let me highlight them, this one and this one, only two equations. You do not need to memorize these equations, but you need to know exactly the meaning of each term, right? And how to use these two equations to solve simple problems. Okay, now we'll try to work out some exercise questions. Okay, and the remaining concepts we will learn next week. Before that, I need to remind you that you have a homework due on 28th February. Okay, don't wait until the last moment and find somebody who has completed the job and copy one to one. Okay, that option is available for you. So if you want to cheat yourself, you can do that. Okay, then you get the maximum marks, but in the exam you are going to fail. Without knowledge, you can't do the exam well, right? So therefore, I just encourage you to work independently. That doesn't mean that you don't need to talk to your friends. You can sit down together with your classmates, work together, learn together, and complete this assignment together. It doesn't matter. Okay. But what I'm asking you not to do is one-to-one copying blindly. That is stupid and it is just cheating yourself. Don't spend such a lot of money and time to cheat yourself. Okay, so that is my advice for you, and I really appreciate if you complete it and learn by yourself, work together, right? Learn from your friends. Okay, so all these assignments that I'm going to give here in this class are for learning. Is learning assessment for learning. Okay, therefore no problem that you work together and learn together. Right. So let's work out few questions from the exercises. So take that exercise sheet first. It is for in week number 4, right? Torsion. Hope that you have this one with you now. So I'll give you a few minutes to download if you don't have it with you. And again, I'm not going to work out all the steps or write all the steps. Sometimes I will not. Okay. Sometimes I will complete everything if I feel that it is necessary. You need to complete by yourself afterwards. Okay. Right. So shall we read this question first together and see how to solve the problem? So what it says, determine the torque T that causes a maximum shearing stress of 45 megapascal. Again, maximum shearing stress 45 megapascal. That is tau max, right? Tau max is 45 megapascal in the hollow cylindrical steel shaft shown. So if the tau max is given, if you want to find the torque T, we know that we have to use torsion formula. Torsion formula says that tau max is equal to Tc over J. So this is what we have learned today, right? So we want to find out the torque T that creates tau max. Therefore, T is equal to tau max into J over C. And in this question, tau max is given and C is the outer diameter, right? It is given. And J, we don't know, because but geometric details are given. Therefore, you can find that. So soon you find J, you can get the answer for part A. So shall we do that first? Do the calculation for the given shaft. First, I can see that we need to find out J. So J for the moment of inertia is pi over 2 times C2 to the power 4 minus C1 to the power 4. We know that, right? So here C2 is the maximum radius, 45 millimeters. So let's find it in millimeters first. Okay, 45 millimeter to the power 4 minus inner one is 30 to the power 4. I have done the calculation. I got this answer, 5.1689 into 10 power 6. 4. So you can convert this one into meter squared before you substitute in the equation. So please write it in meters to the power 4. Okay, so that's it. So now you can write T is equal to tau max into J over C. So everything is known now. So you can find out the answer. Yeah, answer is given to you, right? So do the calculation. You can find the answer. Answer is 5.1689. This is the exact answer into 10 power 3 Newton. Newton per meter. Newton per meter. So that is the part A. Part B, determine the maximum shearing stress caused by the same torque T in a solid cylindrical shaft of the same cross-sectional area. That's a challenging part. I hope that you should be able to do this one as well easily. Determine the maximum shearing stress caused by the same torque T in a solid cylindrical shaft. Now a solid cylindrical shaft with the same cross-sectional area. Okay, so that means we need to find out the details of that solid cylindrical part uh, before we finding out the maximum shear stress. So B, part B. So what we need to find out, the cross-sectional area of the solid circular shaft, which is the same as this shaft given here. So let's say find the cross-sectional area of the hollow shaft of the hollow circular shaft. So let's say it is A. A should be equal to, how to find out the hollow circular shaft area? So what we need to find out this area, right? So we get the area of the bigger circle and subtract from the smaller one. Pi r squared, that is C2 squared minus C1 squared, correct? Okay, so pi into C2 is 45 squared minus 30 squared. Now I get the answer in millimeters squared. So I did the calculation. I got this answer 3.5343 into 10 to the power 3 millimeter squared. Okay, now I need to find out the details of the solid shaft with the same area. Here A1, let's say this is A2, A1 is equal to A2. So I write this one as A1. Okay, now A2, let's assume that the radius is C. Okay, therefore the area is pi C squared. Now this A2 should be equal to A1, right? That means 3.5343 into 10 power 3. So now from this one, you should be able to find out C. So from this C, you do the calculation. I got this answer. C is 33.541 millimeters. So this is the cross-sectional area of a solid circular shaft, which has the same cross-sectional area as the hollow circular shaft. Okay. So now we need to find out the maximum shearing stress in this shaft when we apply the torque, same torque T. Okay. So therefore, you can write that maximum. Is it the maximum shear stress? Yeah, maximum shearing stress. Okay, maximum shear stress, tau max, is equal to TC over J. Okay, where now J is different, right? J is equal to pi over 2 C to the power 4. And then we can simply substitute that in here. It is faster T C over pi by 2 C to the power 4. After simplifying, 2T over pi C to the power 3. Yeah. Okay, so now we know this T, we know C just calculated, therefore we can find out tau max. So I again do the calculation. The answer already given to you here, right? I got this 87.2 into 10 power 6 Pascal. So this is the answer. Okay, let's look at the problem 2. And to go to problem number 2. Says a torque T equals 3 kilonewton meter is applied to the solid bronze cylinder as shown. Okay. Determine the maximum shearing stress. Now it is easy, right? So now we know it is a solid shaft, and for part A, simple. Part A, tau max is equal to Tc over J. Okay, and we know that J is equal to pi over 2 C to the power 4. So T is given, C is 60 millimeters, that is 30 millimeters known, and using J equation we can find this one. Okay, so I think I don't need to work out this question. I leave that part for you and see whether you can get this answer. Part A is easy, so we'll do the part B. Okay, so I'll keep some space for you. Part B, the shearing stress at point D, which lies on a 15 millimeter radius circle drawn on the end of the cylinder. Oh, that is also easy. Why? Because it is a point on a radial position, 15 millimeter radius, inside the, I can say inside, it is like inner surface, right? So we use the generic equation. Tau is equal to T rho over J. So any radial position, I can use this equation. And there, again, the same J, and rho is equal to 15 millimeter radius is 15 millimeters. That's the only difference. Same J, right? Same J. So therefore, again, we know this T, and rho is given, and same J here. So again, you should be able to do that calculation and get this answer. I'll leave that one for you. C says the percent of the torque carried by the portion of the cylinder within the 15 millimeter radius. So that is something new for you. The percent of the torque carried by the portion of the cylinder within the 15 millimeter radius. Now, once we apply this torque 3 kilonewton meter, internally they are going to be resistive torque, right? Resistive torque also 3 kilonewton meter because there are no other torques applied in here. So this resistive torque is created by the shear stress on the surface, right? So we have to find out what percentage of this torque is taken by the inner core, right? So if you can find out the that torque resisted by the inner core, and if you know the total torque, which is 3 kilonewton, we already know 3 kilonewton meter, then the ratio between those two provides the percentage. Okay, so again, we'll first find out the torque resisted by the inner core. Now I'm finding the inside torque, okay, or internal torque. So what you need to do, you take the normal shear stress. Now forget about the outer core. So we take the inner core. Yeah, the diameter is or radius is 15 millimeter. Okay, so we will take in a cross section like this. Okay, and here the radius is or radius diameter 30 millimeters. Okay, and we'll find out the shear stress. We can find out the shear stress tau d as, at that point, tau d, the maximum shear stress, as Td into rho d over Jd. So that means from this one we can find out the resistive torque Td, internal torque Td, as tau d into Jd over rho d. Okay, so now if you find out the values all for these things, you can find out Td. Okay, what is the tau d? That is this tau d here. It is already calculated here. Okay, that is 35.4. So it is the second part B, 35.4 into 10 power 6 to convert into Pascal. This is TD, sorry, tau d, and then JD is the polar moment of inertia of the inner core, within the 15 millimeter radius core. Therefore, it is pi by 2 into 15 into 10 power minus 3. Let me write it in as a decimal one, into 0.015 to the power 4. This is JD divided by rho d. Rho d is the radius. It is 15 millimeters. Okay, so do the calculation, then you will get this answer. I did the calculation, I got 187.5 Newton meter. So this one tells me that the internal torque resisted by the inner core is only 187.5 Newton meter, right? But the whole cross section should be able to resist 3 kilonewton meter, right? This is the internal torque. This is the external torque. The whole cross section should be able to support the same amount. But the inner core is contributing only 187.5. Okay, so if you find out the percentage of what you could say percent of the torque carried by the portion of the cylinder within the 15 millimeter radius, that is the TD over the total torque into 100%. So that means 187.5 divided by the 3 kilonewton 10 power 3 into 100%. So if you simplify, you get this answer 6.25%. Out of 3 kilonewton meter, the inner core can provide only 6.25%. Okay, that means almost 93% of the torque is resisted by the outer surface, outer or hollow circular section, outer section. So even though there are a lot of material in the middle of this shaft, it doesn't contribute that much to resist the torque. Okay, so this is a new knowledge, and we can apply this one to develop very efficient structural members to support torques. So that is the reason why you always find hollow circular shafts in structural members. So you look at your, let's say, if you have an office chair, the office chair vertical shaft is hollow circular, right? So because when we turn around, it is subjected to a torque. So the best shape to support a torque is a cylindrical shape, but hollow circular shape is much better because there's no point of having that middle material which will not support that much of torque, right? Most of the transmission shafts also hollow, for the same reason, right? So because it contributes only a little bit for supporting the load. Therefore, there's no point of having the material in the middle. Okay, so that is why we always use, most of the time, and we use hollow circular shafts. Right. So I think it's very good because we learned something new from this question. And then look at the next question. I think you should be able to do this one because we have done a similar question. So maybe I will quickly guide you through, and then we will stop for today. So what it says, knowing that each portion of the shafts AB, BC, and CD consist of a solid circular rod, determine the shaft in which the maximum shearing stress occurs. B, the magnitude of that stress. Oh, this is, now you should be able to do this one. So if you want to find out the shaft with the maximum shearing stress, because all the dimensions are given sectional dimensions, then what you need to do, you need to find out the internal torque first, and then we use our knowledge about the torsional formula. Tau max is equal to Tc over J. Right? From this one, if you know shears, the torque, internal torque from AB, you can say for shaft AB, find TAB. That is the internal torque. So if you can find out this TAB by observation, I can say that this TAB is equal to 48 Newton meter. Otherwise, you can actually draw a Fibol diagram and then find out what TAB is. So once you know the TAB and also C is diameter is 15 millimeters, that is 7.5 millimeters, sorry, 7.5 millimeters, C. And the J, we know what the J value is, or we can simplify this equation this way, tau max to Tc over pi by 2 c to the power 4, right? That is 2t over pi over c to the power 3. Right? So we already found this t and then c, then we can find out tau max. So this is for AB. And similarly, find out for shaft. PC. What is the tau max for PC? Okay, and next, find out the tau max for CD. Tau max for CD. Same approach. Okay, and then you can see which one has the highest in shear stress. Answer is CD, and the value is 85.8. So I leave that part for you. You should be able to do the problem number 4 as well. I will keep that one for you. Answers are already given to you, therefore you should be able to check with the answer. I cannot see anything difficult there. Okay, right. Problem 5 onwards, you will not be able to do at the moment. You need some support. So next week, I will introduce the remaining concepts, then you can work out those questions. Okay, right. So I'm going to stop here, but I really encourage you to go through the lecture notes again and try out all the questions in the exercises which we have not completed. Okay.